We're launching a new redox potential prediction workflow on Rowan today, and I wanted to illustrate why this is useful by looking at this paper from Dave Nicewicz, a cation radical accelerated SNAR that converts aryl ethers into anilines. So this is the sort of product which you might imagine accessing retrosynthetically through a Chan-Lamb or Buchwald-Hartwig coupling using copper, palladium, nickel, a variety of transition metal catalyzed methods. But what's particularly cool about this is that they take just aryl ethers, which are not a typically used starting material, and there's no metal needed, just this acridinium photocatalyst. And the way that this reaction is thought to work is through a single electron oxidation of the starting material, which makes it much more electrophilic. You could add in the amine and then, sort of re-aromatize and inject the methanol to furnish the desired product. So this is, mild, functional group compatible, cheap materials. So this is a pretty appealing method. And as you can see here, I won't go through the whole paper, but it has quite a nice substrate scope. Although obviously you do have some, requirements for the aryl partner. But look, this looks like something a medicinal chemist would like. But the reason I was attracted to this paper in particular is that to reason about the mechanism, they go ahead and measure a lot of electrochemical redox potentials for the various reaction components, and use this to make arguments about the relative, oxidizability or reducibility of various things. And so this is, if you're the Nicewicz lab and you can easily measure these, then that's a great way to go about thinking about single electron chemistry. But in most cases, you might be running this reaction, but you might not have the right setup or the right know-how to measure these, or you might just not have the time, and you might want to estimate a value for your substrate of how difficult it will be to add or remove electrons. And so in these cases, you can look at sort of reported benchmark values, much like you can look at the Evans pKa table. You can go to this 2016 Sinlet paper, also from the Nicewicz group, and sort of look up where your functional group falls on this chart. So here's the oxidizing chemistry, and here's the reducing chemistry, and you can say, oh, well, I have an aryl amine, it'll probably be somewhere in this range. But these are pretty broad ranges, and the exact redox potential varies a lot by specific substitution. So here for, this alkene, you can see that this paramethoxy beta-methylstyrene anethol is 1.24, so pretty easy to oxidize, relative to alkenes. Whereas changing to fluoro gives you 1.71. And while this is very, very logical, nevertheless, you might struggle to figure out, for a sort of a complex functional group like an imidazole, where does it fall on here, et cetera, et cetera. So there's often you care about your precise compound. And so for this reason, what we've been doing is we've been building out a workflow using semi-empirical methods to make redox potential prediction fast and simple. So let's go ahead and move over to Marvin.js. So I've sketched out 3 of the compounds from the Nicewicz case study here. So I will go here, export from the Marvin.js demo tab to smiles. Here's sort of the collected smile string, and we'll input it here. They spit it out all separated by dots, so you just have to look for the little dots and put them on new lines. And now say submit, so we can look, yep, this looks like propylamine. This looks right for our aryl ether. And then for our product, this also looks correct. Good, good. And so now we can select between oxidation and reduction. In this case, we want to look at oxidation. And then we'll keep the default rapid mode, which is the one we've optimized the most. So we'll say submit workflow, and now these are going to run. So this one is now running. And we can see that this only took 5 seconds, and we predict oxidation potential of 1.53 volts. So let's go ahead and compare here. So this is 1.60, so that's a nice good prediction. That's the mean absolute error for these is generally about 0.3 volts. You can't get much better even if you go to expensive double hybrid methods. There's too much solvent error. So we're able to get approximately useful answers and do it many, many orders of magnitude faster than you get with ab initio methods. We can also sort of look at how things change. So this is the cation. This is the neutral structure, and now we can view the cation. You see the bond lengths change a little bit, but it looks pretty similar because it is the same compound. And now the other two have finished. So this now has a much lower oxidation potential. It's much easier to take electrons out of this, which makes sense because the amine is an electron donating group, so this ring is now very electron rich, much readier to give up electrons. That's characteristic of anilines. This took 25 seconds because it's a larger molecule. And now this here it predicts is also, about as easy as the original aryl ether to oxidize. This is 1.52 volts. And if we look over here, we can see that this is actually predicted to be 1.75. So this should be a good amount more difficult to oxidize. And this is, I think, a pattern which is seen and remarked on in the literature, that solvation errors are often bigger for smaller molecules. So this is a little inaccurate, and it may just be an intrinsic error. So until we get better solvent methods, we are going to still have some error in these calculations. But nevertheless, I think these computed redox potentials can be very useful and are fast enough to be a conceptual aid for organic chemists of all stripes. So that's the Rowan redox potential workflow. I hope that this is useful for you and your science. Happy computing.